This is part 3 in a series of videos making sense of organic mechanisms, this time focusing on radical reactions. And like the previous two, rather than going step by step through a particular mechanism that you can just memorize, the aim here will be to build a general confidence in the kind of things that can happen in a radical reaction and how that's represented using curly arrows. Radical reactions have a key difference to the mechanisms for most other reactions, and that's that you see these curly arrows that have just half a head. These show the movement of one electron compared to the pairs of electrons that we've been moving around in the previous two videos with the curly arrow with a whole head. And with just one electron moving, this means bond breaking and bond forming looks rather different. So for instance, forming a bond, instead of one arrow bringing a pair of electrons to form a bond, we're going to need to have two arrows, each bringing one electron to give the pair of electrons that are going to be shared when a covalent bond forms. And likewise, bond breaking, we've got to take a pair of electrons out of the bond. So rather than one arrow with the whole head taking both electrons away, we're going to need two of these half-headed arrows each taking one electron away in order to break the bond. We saw in the previous two videos that the curly arrows, as well as making and breaking bonds, also cause changes in charge. So for instance, if we break a CBr bond with a whole-headed arrow, so in this case both the shared pair going onto the bromine, we lose the bond, but we also end up with ions. And so just to explain exactly what's going on here, if you think about it, the shared pair in the CBr bond, one of those electrons came from the carbon and one from the bromine. So when both of them go onto the bromine, that means the carbon is losing the electron that it had in that shared pair. When you lose an electron, you become a positive ion, or you become one step more positive. In this case, carbon going from neutral to a 1+ ion. And likewise, the bromine, when that pair moves onto it, is actually gaining an electron that came from the carbon. So it ends up with one more electron in its outer shell, and so therefore becomes one step more negative, in this case going from a neutral charge to a negative ion. With half-headed arrows, something slightly different happens. So if we consider breaking the CBr bond again, this time with the half-headed arrows, the pair of electrons are moving out from the bond, so we have the bond disappearing. But this time, instead of ions, we get what are called radicals. And the best way of picturing what's going on here is where the C and the Br were sharing a pair of electrons, each atom is simply getting its own electron back again. So nothing has gained or lost an electron, therefore no changes in charge have occurred. Let's take a moment here to make sure we know what we mean by a radical. And the definition you should be able to recall from memory is that a radical is a chemical species with one or more unpaired electrons, not a lone pair of electrons, an unpaired electron. And to just give a few examples of that, if we take a single chlorine atom, 7 electrons in the outer shell of chlorine, if we pop those in, 3 pairs, 1 unpaired electron shown with the blue arrow there. And it's not just individual atoms. If we take an OH group, not a hydroxide ion OH-, but just OH, we look at the dot cross diagram. Again, we see that there'll be an unpaired electron shown with the blue arrow there. So an OH group, hydroxyl as it could be called, group is a radical if it's on its own. And even bigger than that, if we take a CH3 group, a methyl group, so in other words sort of methane having lost a hydrogen, do the dot cross diagram for that, you'll see that one of the 4 electrons in carbon's outer shell is unpaired. It's not taking part in a bond. It's an unpaired electron. So a CH3 group is a radical, a methyl radical. There are 3 main types of event that can happen in a radical reaction, and it'll help us make sense of radical reactions if we understand those. They're called initiation, propagation, and termination, and we'll look at each one of those in turn. Initiation, first of all, and to understand what we mean by initiation, we can compare the reactants and the products. And the key feature here is that for initiation step in a radical reaction, the reactants won't include any radicals, whereas the products definitely will. Looking at an example of that, if we start with Cl2, chlorine molecule, and expose it to sufficient energy to break the bond, often from electromagnetic radiation such as ultraviolet light, we can get two separate chlorine atoms, each of them a radical. So this is taking a non-radical, the Cl2 molecule, and turning it into radicals, the two separate chlorine atoms. If we look at the curly arrows for that, the half-headed arrow, two of them starting from the bond, one going to the chlorine at each end of the bond, and that'll give us our two radicals. Just note here, I've deliberately not drawn a dot next to the chlorine atoms that are the product. You often will see radicals drawn that way, with the dot representing the unpaired electron, but you often won't have a dot shown. And it's important to note it's not the dot that makes it a radical. The only way to be sure something is or isn't a radical is by thinking of the dot cross diagram in the outer shell and whether there is an unpaired electron or not. So here's an example for you to just check that you've got the idea of initiation. If we have bromomethane and we have an initiation step occurring, it would be the CBr bond that breaks. It's always the weakest bond that breaks, and if you compare the bond enthalpies for CH and CBr bonds are weaker. So why don't you pause the video and sketch out what the curly arrow diagram would look like for an initiation step involving the CBr bond breaking in bromomethane. And if we draw the relevant bonds, we should have a half-headed arrow heading out to the carbon and to the bromine from the CBr bond, and that gives us our methyl radical and a bromine radical. Each of those would have an unpaired electron in its outer shell. Second kind of event that can happen in radical reactions is called a propagation step. What do we mean by that? Well, if we compare the reactants and the products, in a propagation step the reactants will contain a radical and so will the products. So propagation steps maintain the presence of radicals in the reaction. If we take an example of that to make a bit of sense of it, this has a methyl radical, CH3, reacting with a chlorine molecule. We get chloromethane as one product, a perfectly stable molecule, and a chlorine radical. So we started with a methyl radical, we've carried out a chemical change, but we've ended up with another radical, the chlorine atom. And if we look at the curly arrows here, there's a very particular way, and so it's worth you spending a little bit of time looking at this, of how radicals react with molecules. And they do it by kind of grabbing an atom off the molecule they're reacting with. So the radical's got its unpaired electron, and it'll use that to start a bond forming to an atom in the molecule that it's attacking. Of course, that only brings one electron into the space between the two atoms. A bond needs a pair of electrons being shared. So we get a kind of exchange of loyalty here. The chlorine, where it was taking part in the Cl2 molecule, so to speak, transfers its electron round to now be involved in that bond to the radical, which starts that CL-Cl bond breaking, but of course that's a pair of electrons, so there is another electron in that bond, and that returns to the chlorine at the other end of the bond, so that chlorine kind of gets its electron back from that share. So we have a sort of a tale of relationship movement here. The two chlorines were sharing together at the beginning, but at the end we now have a new share between one of the chlorines and the carbon in the methyl radical, and we've now got that other chlorine on its own. So one for you to try, a propagation step involving a bromine atom, so a radical, with a methane molecule. Have a think, what could you draw with curly arrows to show a propagation step that could occur between those two species? So if we draw out the structures here and use our curly arrows, the bromine radical can use its unpaired electron to start a bond forming to one of the hydrogens on the CH4, causing the CH bond to break. The hydrogen transferring its electron from that share with the carbon round to a new share with the bromine, and the carbon getting its electron back. That then gives us an HBr molecule as shown, and a new radical, a CH3. So this fits the model of propagation. We had a radical in the reactants, the bromine atom. we've got a radical in the products, the CH3. The final type of event we need to consider for radical reactions is termination steps. And so let's look at what we mean by that. Again, we can compare reactants and products. In a termination step of a radical reaction, we have radicals in the reactants, but our products no longer contain radicals. So termination steps remove radicals from the reaction. We can illustrate this with an example. Two methyl radicals reacting to now make a non-radical, an ethane molecule. There's no unpaired electrons if you look at the dot cross diagram of ethane. And if we look at the curly arrows here, we've got these two radicals, each with their unpaired electron. Well, they can simply put those into a shared pair between them, forming a covalent bond joining the two radicals together. So we've gone from radicals to non-radicals. So here's one for you to check that you've got this. See if you can use curly arrows to show a termination step that could occur between this chlorine atom and this ethyl group. And if we draw out the structures, we've got the two unpaired electrons there, so each one can move into the space between the two, the chlorine atom and the carbon atom there, to make a shared pair, a covalent bond, and we now end up with chloroethane, which is not a radical, no unpaired electrons. What follows now will be a series of challenges which might involve one or more of the steps we've just been mentioning, the initiation, propagation and termination. So in each case you'll see a reaction and you need to pause and consider what kind of radical processes could be taking part in this. So here's your first one. You've got a 5-carbon chain with an unpaired electron on the middle carbon reacting with a bromine molecule. So your challenge is to come up with the curly arrows and also the product that you'll therefore get from this reaction. Pause the video and see what you can come up with. So if we take the two reacting species, this is going to be a propagation step, a radical reacting with a molecule, snatching an atom away. So it can use its unpaired electron to form a bond to the bromine, with the bromine-bromine bond breaking in the way shown. And that's going to give us what is actually 3-bromopentane and a bromine radical, so a propagation step. The next challenge for you is rather more involved. The reaction between trichloromethane, CHCl3, and chlorine to make tetrachloromethane, CCl4, and hydrogen chloride. Now if you look at this, all of those are stable molecules. None of them would have an unpaired electron in its outer shell, so we don't have any radicals shown here, and yet it is going to be a radical mechanism. The HV over the arrow says energy from electromagnetic radiation, so we're going to be exposing this to UV light in order to form radicals initially. And just to help you decide what to do, when we form radicals, it's normally the weakest bond that breaks. So I've shown you bond enthalpies there for the bonds in the reactant. So why don't you pause the video, see if you can suggest a multi-step process that will carry out the reaction shown here via a radical mechanism. Okay, let's look what's going on. The weakest bond is between the two chlorines in the Cl2. So the most likely initiation step would be the formation of two chlorine radicals from the Cl2 molecule as shown, and that's what you should suggest. Always suggest the weakest bond breaking for initiation. We've now got ourselves some radicals, so those could react with something else, and the key thing is to decide what could they react with that would take us toward our product. There's no point having those chlorine radicals reacting with another Cl2 molecule, because that wouldn't bring about any change in the direction of the products we want. So the thing that they can react with would be one of the trichloromethane molecules, and the only sensible atom for them to grab off that would be the hydrogen. Now that's not to say that chlorine radical couldn't react grabbing a chlorine off the CHCl3, but if it did, we would just reform Cl2, and we wouldn't be really putting ourselves in a position to be adding extra chlorines to the CHCl3. In fact, we'd be taking one off. Now that wouldn't take us in the direction of our product. So although it would and probably could and probably would be happening in a radical reaction, there's no point us presenting that. So we'll do what is most productive here, and we can have that chlorine radical grabbing a hydrogen off the CHCl3 as shown, typical propagation step, and that's going to give us our HCl, one of the two products, and a new radical, the CCl3. That then can go on and react with something. What can it react with in order to make CCl4? Well, what there's going to be lots of available if you've mixed up a bunch of trichloromethane and chlorine is chlorine molecules. So we can have another typical propagation step where that CCl3 radical grabs a chlorine from the Cl2, and that now takes us to our CCl4 and a chlorine radical, which of course can then take part in the previous step again, and this can go on over and over and over. It could be that you got this far and then suggested the CCl3 reacting with a chlorine radical in a termination step to make the CCl4 that way. And of course that is a perfectly feasible thing that could happen to make the CCl4. In terms of probability, there'll be less chlorine radicals around than the chlorine that was mixed in. So it's probably more likely to bump into a Cl2 molecule than a chlorine radical. But nonetheless, the termination reaction with a chlorine radical is possible. For your next challenge, an unusual looking reaction between hydrogen peroxide and hydrogen bromide. It's actually not an organic reaction at all, but it can nonetheless proceed via a radical mechanism, and we can use the half-headed curly arrows in the same way. As a clue to get you going, we don't have any radicals in the reactants, so if there's going to be a radical reaction we need to form radicals, and the single bond between two oxygens in a peroxide is a particularly weak bond. Why don't you pause the video and see if you can sketch out some steps that would take us to the desired products here. So we can start with an initiation step that breaks the O single bond O bond as shown, and that will give us two hydroxyl radicals. And those hydroxyl radicals are now very reactive. They'll react with pretty much anything they bump into, but in terms of something that's going to give us the products that we're actually looking for, the most sensible thing will be for it to be reacting with the HBr, and specifically to be grabbing the H atom off. There wouldn't be any point showing it grabbing the Br because the HOBr is nothing to do with the products that we're forming. So if we do this propagation style step with the hydroxyl radical grabbing a hydrogen, we'll get H2O, which was one of the products, and a bromine radical, and that's the other one. Now, of course, having formed two hydroxyl radicals, that second step could happen twice, and that's what the balanced equation shows. But we don't need to draw out the step twice. And a final challenge for you, a bromine radical reacting with ethene to make the species shown. Slightly different here in terms of we're not grabbing an electron off. We've got a carbon-carbon double bond, so we can actually do addition, if you remember, by turning that to a single bond and adding things on. So see if you can work out some curly arrows here that will allow you to produce that product. And if we take the structures here, we can form a bond between the bromine and the carbon, the bromine using its unpaired electron, and then one electron coming out of a bond in the double bond. It would be the pi bond that breaks to form that new CBr bond, and the other electron in that pair of electrons in the pi bond going onto the other carbon. So that's going to give us our new CBr bond. The double bonds become a single bond, and we have a radical now up at on the carbon at the other end of the C11C to where the bromine joined.